morning, afternoon, evening, and welcome. My name is Thi-Hien Nguyen, and I am your host and show producer today. I want to begin thanking all of you participating in this show, Series 29, Stellar Detective, the Formation of Planets, Stars, and Supermassive Black Holes, and Interstellar Extinctions. Your research is so much needed right now of facilitating access to the benefits of space exploration, science, technology, and STEM education with UNOSA's Space for Women network. And your efforts ensure the mentors and mentees' understanding of the issues and concerns. So I want to know that your research and philanthropic work is deeply appreciated. Welcome our special superstars guest today, Dr. Parshati Patel, an astrophysics, Dr. Abhijeet Borkar, a postdoctoral researcher, and our UNOSA Space for Women mentor today is Dr. Elena Kilpio. Today's show will be moderated from Israel by Dr. Anna Heller. She's an astrophysics. Anna is an expert also in nanosatellites. She holds a PhD degree in astrophysics, a master's degree in geophysics and planetary science from Tel Aviv University, Israel, in astronomy for the National University of La Plata, Argentina. And welcome to our co-host, Malak Trabelsi today. So without further ado, the floor is all yours, Anna.
Thank you, Thian. Hola, shalom, shalom to everybody. Welcome to this new section of Space for Women. I am really very delighted to be with you, and this time like a mentor, moderator, as I am very excited. All the other times I was listening to you, now I am going to be together to you. And I want to say it's really my honor to be with you and to be part of this program. But the most important thing that we have today, 3 outstanding speakers, and they will present exciting topics in astrophysics. And because I am myself an astrophysicist, and I'm very curious to hear what they are going to tell us. So I propose we will start right now. And we will start with Dr. Parshati Patel. Let me tell you a little about her. It's not so little. She has a lot what to say. And Dr. Parshati will present about stellar detectives, the formation of stars and planets. She is originally from India. She is an astrophysicist, science communicator, educator, and researcher based in London, Ontario, Canada. She is the educational outreach and communication specialist at the Institute for Air and Space Exploration at Western University. She received her MSc and her PhD in astronomy and planetary sciences and exploration from Western University. She graduated BSc in astronomy and physics from the University of Toronto. Fantastic. Dr. Patel initiated various educational programs at Western University, and also she's co-founded the program of color in STEAM, science, technology, engineering, arts, mathematics, and medicine in Canada in 2018. And she also have many honors and awards. Just to short them all for you, because the list is very long. She got the Pride of Gujarat by the Gujarati Public Affairs Council of India. I was looking at the city, beautiful. I hope to be there someday. And then she has the Award of Excellent Operation by Park and Recreation of Ontario, and the Social Media Prize by the International Astronomical Union in February 2019. So we want to hear what you want to say. So Dr. Parshati, you have the audience. Go on.
Thank you very much, both of you, for hosting this and introducing me. I am going to share my screen, but while I do, I would like to wish everyone who are celebrating Diwali very happy Diwali to everyone. And I always like to start off with talking about kind of where I started. I like to call myself a stellar detective. Hopefully, you guys can see my screen. I would, I always like to start off with kind of where I started. And the reason for that is because, a lot of people think that, you just come to know about astronomy like in your undergrad, especially in India, or your master's, and you kind of start from there. For me, actually, I was introduced to space during a visit to a planetarium. And one of the cool things about this particular visit was that before that, I had looked at the sky, but because I lived in a city that was a little bit polluted, but at the same time I was living in the core of the city. So, I couldn't really see a lot of stars. And so I ended up kind of learning about the galaxies and what's out there at the planetarium. And since then, I was just kind of obsessed with space. I just wanted to learn more and more. And the reason why I talk about being a stellar detective is because when I was young, I used to watch this crime detective show, which I think is one of the longest running shows in India. Anyways, I always wanted to be a detective because I thought that was so cool to solve mysteries and have little clues and put a puzzle together. And I think I didn't realize that a lot of that kind of solving I was doing while I was doing a master's and my PhD. And so at the end of it, I started calling myself a stellar detective because I still got to solve mysteries. It was just not here on Earth. It wasn't criminal in nature, but it was the mysteries that existed out there. And so, one of the things that always fascinated me when I was young was looking at the planets and looking at our sun. And what I always thought about was how do they form? What are the things that are needed for these kinds of amazing objects to form out of, and so when I started my bachelor's, I always craved for wanting to be part of research projects where I'm learning all about how planets and stars are forming. Though I love galaxies and black holes and all of that stuff is still amazing. But my heart always lied at star and planet formation. So that's kind of what I did. And today I'm going to introduce something that I did during my PhD. As Anna mentioned, I now am a science communicator, but I do translate a lot of research that other people do to the public and to the students. So, this is kind of my PhD project I'm going to talk about today. And, feel free to ask me any questions you may have about my current job that I have as a science communicator. So let's get started. So my first slide. So this is what we call star forming regions or stellar nurseries. These are the regions in the night sky that sometimes you're able to actually see with a small telescope, and these are the places where you have the perfect storm, as you can see, or perfect amount of ingredients, the material that you need for stars and planets to form. And they're beautiful to look at, but they're also very, very large. They're way larger than what our brains can actually imagine in many ways. But what they really have are these ingredients, gas, dust, a lot of shock waves that pass through them that actually trigger these things called star formation. And that process is very interesting. We humans only live for around, on average 80 to 90 years. These things takes hundreds and millions of years to actually form. And so it's very interesting that as someone who wants to learn how these objects are forming, you're really piecing these puzzles together. So, throughout the presentation, I'll be mentioning a lot about what detectives do and kind of talking about how it's very similar in many ways. And this particular regions, the pictures you're seeing are these snapshots that you have. This is a snapshot of Orion Nebula right here, and you're seeing what existed at one point of time, but you're now trying to take snapshots of these objects and you're trying to put together what exactly happens when a star or planets and stars actually form. And so, they not only look magnificent, but they're an amazing place to get started on when and how and where these objects are actually forming. So let's start and kind of look at how it goes from that magnificent big cloud of gas and dust to an actual star. So in first phase of what actually happens in these objects is that you have this giant cloud of gas and dust, and within those clouds you start getting these tiny clumps. And in this slide you will see that there is at the bottom this number that will show you the size. So when I meant 200,000 AU, and AU is in unit of the average distance between Earth and Sun. So you can imagine, Earth and Sun is a certain distance, you multiply that by 200,000, that's how big this particular cloud generally is. And this is kind of an average number, but you can imagine the big, the vast thing that it is. You cannot even generally, think about how big that would be. But these are massive objects, and within those massive objects, you can get these tiny, tiny clumps, or we like to call it dense cores, because we are always very literal about it. We astronomers are great at that. And these cores are very much where these stars will eventually form. And so that material that is actually coming together very close in this dense core, the moment it starts getting bigger and bigger, it goes through what we call a gravitational collapse. Basically, the gravity is kind of taking over, pulling everything that's around it to its center. And you can see the change in the size of this object. It went from 200,000, which obviously contains a lot of dense cores, to this tiny one area of around 10,000 AU. And this is kind of when we start our timer in terms of, okay, the star is now starting to form. And eventually over time, you can see that within, depending on the mass of that core, can get anywhere from 10,000 years to 100,000 years for that to go from that dense core to this lovely looking star that you generally cannot see because it's covered by dust and gas around it. And that can happen in form of a disk, which I have shown here, but it can also have this envelope of material, which is basically a lot of gas and dust that you can hardly even see what is going on the inside. And sometimes, depending on the size of the object, you can also get these lovely bipolar flows. So what these are basically, jets of material coming out from the object. It can be in both directions, could be only in one direction, just depends on the star and how it's forming. And then you go on to the next step, and over time, again, 100,000, 300,000, sometimes it can take longer depending on the size of the object. You start getting rid of that particular envelope. Everything is settling down. You now have something in the middle that can be called a star or protostar. And then on the surrounding areas, you now have a disk of a lot of gas and dust. And believe it or not, this is the site where the planets are forming or going to form in its later stage. And you can see that, this goes from the 10,000 AU to 100 AU. So, it kind of squeezes down a lot when it comes to the size. And then as you keep going, over time, you spend, again, a lot of time. Over time, you get rid of all that gas, and, you have all the dust that settles into these rings where eventually a lot of these planets form. A lot of the planets get kicked out, and you kind of end up with a lovely system just like our solar system. And this is this phase where we call it a pre-main sequence star. So this is still not a place where it's burning hydrogen in the core. So it hasn't really ignited the hydrogen in the core. So it's not like our sun yet, but it still takes time to get to that phase. And eventually, after such a long time, again, depending on the size of the object, you end up with a central star and some or a lot of planets, depending on what you're looking at. But the interesting thing is goes from this vast, massive object to this tiny, lovely little star, and then the planets around it. And even though it looks like, these are a lot of different stages and we don't live that long to see them, how do we know about these? And that's because we actually have these amazing things called telescope that we use in the night sky and take pictures. And so here's again the picture of the Orion Nebula that I showed you guys before, but now with an overlay of these tiny, tiny things called propyloids, and they're not tiny, even though in the vastness of the object, it does look like that. These are basically these young stars that are starting to form. And so you can see here, there's a wide variety of those. There are, some that have the single jet. There are some that just have the disk. I particularly love this one right here because, it's a very thin disk. There's a central star, but they all vary. And the most interesting part is that you take pictures of each of these snapshots and try to learn different things from it. For example, I was very much interested in learning disks. And so I would take the pictures, or I would look at the stars that just have disks around them, just because it's so much easier for me to understand those. And, one of the neat things is nowadays that we have so much technology that we're actually able to, develop these kinds of videos where you're actually diving into the Orion Nebula. And, we have acquired so much data that we're able to see that if we were to hop in to, let's say a spaceship that would actually be able to travel this fast through these stars, this is what it would look like. And it's an amazing, feat of technology that we are able to do these, and we're able to actually visualize and see, for example, this particular object is my favorite is because, you can see that this object has formed, but you can see that there are shock waves that there are going through that particular system, which generally triggers star formation, and in, how it reacts to it. And so this is a particularly very interesting video that I always like to show because it just shows how amazing, how amazing of star technologies that we are able to actually get all this information, but then process and put it in the format that we would be able to imagine ourselves being part of that. And so let's say, we have these tons of different stars that you see in the night sky. Do they all look the same? They all look the same, or may look the same to our eyes, but in fact, they're very different from each other. And so I like to call these flavors of stars because it makes sense to put them in certain categories. We like to put things in categories to be able to understand them better. And so, we have lots of these categories for the kinds of stars depending on their masses. So, if you look from left to right, you have, the smallest one, which is very dim and red in color, to the biggest that goes to O. And I was always intrigued. Our sun is actually the G-type star that I pointed right here. And I particularly always liked the massive stars. And one of the reasons for that was that massive stars are very interesting because they're bigger. And the most interesting part about them is that as they live through their life, they actually get over everything really fast compared to something like our sun. So for example, sun would, still burn hydrogen in its core for, 4-ish billion years before it runs out of it and goes to the next phase. Massive stars do that very quickly. Their temperatures are very, very high, and they're able to basically run through their fuel faster than the smaller stars. And so what makes that interesting is that they are actually running through their phases faster than any other star that we know of. And that makes them interesting in a way that if we are not able to see them grow and, go through their life and die, why not take the ones that are going through it faster and take the snapshots and try to understand what they're doing. And the most interesting part is that their temperature ranges on the surface 30, 40, 50,000 degrees. And their masses can go up to 50, 60 times the mass of the sun. I was particularly interested in B-type stars, and I'll talk a tad bit about it in the upcoming slides. But what I wanted to kind of give you guys an overview about was the fact that, we went from that lovely cloud of gas and dust to a star, and that is what happens at this average star stage. And it depends again on your mass. If you are an average low mass star, you're taking your time to go through phases. But if you're a massive star, kind of do it at a higher speed. And so for an average star, you would go through, your burning of hydrogen, you'll become a red giant, well, you will swell up, and then you will shed all your material into, the outer layers into a planetary nebula, and you will be left with a white dwarf. But if you're a massive star, what really happens, and Abhijit is going to touch on this a bit in his presentation, is the star becomes red giant after it burns up its fuel, and then it ends up in a supernova, and then you can have one of the two things left. You can have a neutron star, you can have a black hole. We see there are other ways of forming black holes as well, and which I hope Abhijit will talk about in his presentation. I'm going to quickly touch on what I really liked studying about these stars, and the fact that this is an artist's conception, this is not an actual picture, but what it really shows you is that these stars are forming in the center, and you have this lovely disk around it. In this particular picture, you can see it's blocking most of the star, right? And we generally don't really see the star itself. We're seeing all that dust around it that's covering it. But we do have light from the dust, and sometimes a tad bit of light from the star as well. And I really wanted to know how the disk interacts with the star, which, this is obviously the disk eventually that's going to form the planets, and how these stars are actually forming, because we're not really able to see the formation process. I really wanted to know what happens to them in, behind that lovely thick cloud. And so for my particular research, what I was really doing was, if I was able to take a star and the disk around it and like cut it in half, this is what it would look like. You would have a lovely star in the center. And because, I like to study the massive stars, they're so hot, they even evaporate the dust. So you would get a tiny region around the star where you would not have anything except gas. So there won't be any dust. So there's like this gaseous disk around it before you start getting all of these, dusty material, and you end up with a mixture of dust and gas, where eventually, all the dust kind of forms into planets, and all the gas basically evaporates. And so the way I kind of studied those was using, one of the most loveliest telescope, the Canada France Hawaii telescope, as well as other telescopes from across the world, where I was able to get a lot of data for a lot of these massive stars with, a lot of this material that is roaming around it. I was able to get the light from it. And we astronomers like to study the stars in very many different wavelengths. And what I mean by that is, for example, if you ever microwave your food, you don't really see the microwaves, but they exist. We are not sensitive to it, so we're not able to see it. Same with X-rays. I particularly like to study the visible range, which is what we are able to see, as was the infrared range. And the way we actually do that is we take the light from this particular star or many stars and split them. And we use something like called prism, or in this way it's kind of showing to you how it would look like on a larger scale if you were to do it. But this is what it would look like. You would get the light would be split into many colors. But what's the most interesting part is that when you do that, you see a lot of these dark lines, or sometimes you're missing them, sometimes you're seeing them very bright, and these are actually signatures. They are exactly like our thumbprints, like detectives like to take their fingerprints and make sure they're matching it to the criminal, to ensure that it's the same person who did the robbery. And it's kind of similar in that way, that when you're looking at these spectra, each of the element has its own fingerprint. It's very unique to them. And so, here's an example. We go from like an O-type star to an M-type star, just the flavors that I showed you before. And you go through that, spectrum, and you're seeing a lot of these dark lines, and each of these actually correspond to a lot of these different elements. We have hydrogen, we have helium, we have iron, we have, so many more down here, calcium, magnesium. can think of all of the things that you find here on Earth are found everywhere else in the universe. And, so you can actually find a lot of these are in and around the stars. And what I, as an astrophysicist or a computational astrophysicist, as I like to say, what I was doing is I was taking all of this data. So again, here's another example. On the top, we have an A-type star, which is close to massive, not exactly massive. And on the bottom, we have a G-type star, which is like a star like our sun. And you compare the amount of light that's coming through them, for example, the one at the bottom, and you look at their strengths. How strong is this particular line, or how strong is this particular line? You look at those and you compare the two. And just by looking at this red and blue, you can see that they're very different, which means that the elements in and around those objects are very different. And so by understanding which elements are present, we can actually figure out what we could understand in terms of where this material is, how hot it is, what amount of material exists. Is it very heavily made of hydrogen, helium, calcium, iron, all of these different kinds of things. And what I did was, when I would get all of these data from all the stars, I really need to have that understanding of, okay, what is happening? Luckily, we live in an era where, we have a lot of these computers that we can use to simulate what it would be like if I were to take a rocket ship and fly near this particular star that I'm studying. And to be able to do that, I was able to use a computational model that basically simulated what it would look like. So for example, in this picture, I have a star, which is a B-type star that I was able to generate in my computer, along with the disk around it. And, with the data that I have from the observations, I can figure out, if this particular star would produce the same kind of data, and then compare the two and see, okay, looks like I'm missing a lot of hydrogen here, or looks like I don't have enough density, I don't have the right temperature. And it's literally like sitting in front of, an airplane cockpit, and you're like turning all of these knobs to figure out, what's the exact way of trying to make this particular star and disk that you're seeing in the night sky. And so, believe it or not, during my 4 years of PhD, I was able to study 4 stars in detail. So, it's a long process. I ran around, I think it was around 8,500 models during my 4 years of my PhD. And so it takes a lot of time to try and understand these massive objects that are interesting, but at the same time, very elusive in many ways, because, we had to figure out indirect ways to try to understand what is happening to the star, how close the disk is to the star. Is the disk affecting how the star is forming? Is the star affecting how the disk is forming? All of those kinds of questions. And really, we only need 2 things. We need a computational model that's able to, kind of predict what it would look like if I were to put this in a sky. And then the other is the observational models, or I would say observations combined with the models. And we're able to figure out what is happening to the star and the disk just by comparing the 2 things. And so, I really enjoyed learning that process, and throughout our research, we were able to figure out that massive stars, as interesting as they are, they form in a very, very different way than what our sun would. And that's just because more massive stars do not have what we call magnetic fields around them. They do, but it's not strong enough to actually be able to accumulate all the material from the disk onto the star. And it was a new way of thinking, because everyone was like, oh, it works for our sun, it should work for massive stars. But we found that it wasn't really the case. So, it took me 4 years to figure that one line out. But that's the beauty of research. It takes you a while, but when you do figure out, it's an amazing feeling. So I'm going to stop here. I do see a lot of questions already in the chat. And so, if you have any questions, feel free to put in the chat. You can always reach me at one of these things if you have more questions that I wasn't able to answer today. So I'm going to stop sharing and start taking your questions.
So after this very interesting presentation that myself, I have a lot of questions. Maybe we'll be in contact later. I would like to present to you now Dr. Abhijit. Do I say it good? Borkar from Prague, the Czech Republic. He is an astrophysicist too, postdoctoral researcher at the Astronomical Institute of the Czech Academy of Sciences. Dr. Abhijit is currently working on the study of galactic nuclei and supermassive black holes. Pay attention, particularly using radio interferometric techniques, very interesting. And his research interests include the study of Sagittarius A, supermassive black hole in the center of the Milky Way. Pay attention, don't be afraid. And the formation of the supermassive black holes at the center of galaxies in general, and also star formation in galaxies, again, something similar like Dr. Parshati. So he will be talking today about supermassive black holes and how to find them. Go ahead.
Thank you. So I will be talking about supermassive black holes today, and let me share my screen. Let me start by talking about black holes. Everybody almost knows about black holes. People have heard about them. People have seen this kind of nice illustrations that have been shown in different press releases, in magazines, newspaper articles, and science articles all the time. And these black holes have fascinated everyone from scientists to public alike. And especially if you have seen the movie Interstellar in 2014, that features one of the now famous black holes. It was called Gargantua, and it was supposed to be a supermassive black hole. So this has really made black holes famous to the public. So that's something that I will be talking about today. But to begin with, what exactly are black holes? And the question has been sort of plagued scientists for a long time. And the concept of black holes was already postulated several hundred years ago. About 200 years ago, people thought of black holes and the concept of black holes. So for this, you need to understand the concept of escape velocity. So when you throw a ball up in the air, it comes down eventually in a few seconds. So the faster you throw, the higher it gets, but eventually it comes down. But there is a limit to that. The limit is called escape velocity, that if you throw the ball faster than this speed, then the ball will not come back at all. So what you need to do is, if you need to escape the gravity of the Earth, you need to throw something really, really fast. And we do that using rockets, because you need to provide very large amount of fuel and a large amount of speed for the object so that it leaves the escape velocity of the Earth. Now then, people thought, okay, escape velocity is related to the mass of the Earth. And if you have a bigger mass, you would have a bigger escape velocity. And if you have a smaller mass, you will have smaller escape velocity. So if you have seen the videos of Apollo landing, to get astronauts to the moon, they had to be going on these massive rockets from Earth. But when they landed on the moon, to come back, they did not need any massive rockets, because the moon is much smaller and it has a much smaller mass. So they did not need as much rocket fuel to escape the velocity of the moon. So instead, they could just get out of the surface of the moon just with a small spaceship. So that's something that you can think of in terms of escape velocity, that the more massive the object, the more difficult it is to escape the gravitation of that object. So 200 years ago, scientists thought of, can there be an object in the universe for which the escape velocity is more than the speed of light? And if that happens, if the object is so big and so massive that even if to get out of the gravity of that object, you will need to travel faster than the speed of light, then even light will not be able to come out of that object, and that object will appear dark. So this was one of the first ideas of a black hole. But then came Einstein, and he changed our ideas of what gravity is. So instead of gravity being a force, he theorized that gravity is something that happens due to any mass, and the presence of this mass bends the space-time curvature around it. And heavier the object, the more mass it has, the more it bends the space-time. And how it bends the space-time determines how much escape velocity it has. But the crucial difference is that it's not simply the total mass of the object that changes the space-time, but also the density, so how compact it is. So if you have an object which is very, very massive and very compact, then it will bend the space-time around it very, very rapidly. And so that is sort of something that gives rise to the concept of a black hole, that if you have any object, that if you compress it quite strongly so that it falls into a very compact region, then it will curve the space-time around it so much that even light cannot escape outside it. And the other thing that Einstein also taught us is that in our universe, nothing can travel faster than the speed of light. So if the escape velocity of the object becomes the speed of light, then nothing can come out of it. So eventually that will form a black hole. And so you can essentially turn any object into a black hole. If you take our sun and you compress the sun to the size of a 2 kilometer radius bowl, then the sun will turn into a black hole. Or if you take our Earth and if you compress the Earth to a size of a grapefruit, then it will turn into a black hole also. Of course, we cannot do that in our laboratories, partly because we don't have any machines that could turn any random object into a black hole. We just don't have that kind of physics available to us. But that does not mean that black holes are not real. Black holes do form in the universe. And as Parshati had mentioned, that the way to form black holes, one of the ways is to have star formation. And if you have a massive star, which is more than 20 times the mass of the sun, it eventually grows into what is called as a red supergiant. And this red supergiant lives its life very, very quickly, and then ends its life in a massive supernova event, which throws off all the outer layers of this star. And what remains in the core actually collapses into a black hole. So this is how usually black holes are formed in the universe. And we have seen many evidences of these black holes. So there are what are known as the X-ray binary systems, which are binary systems are where two stars or two objects are orbiting around each other. And there are certain systems where there is a normal star that is orbiting around a black hole. And the black hole attracts a lot of material from the surface of the star. So all the gas in the atmosphere of the star is attracted by the black hole, and it forms this very bright disk around it called the accretion disk. And so this accretion disk then glows very bright, and we can see that glowing accretion disk in X-rays. And so this system is then called as the X-ray binary system. And other ways we have detected these black holes is through the gravitational waves. When two black holes are orbiting around each other in a binary system, they will eventually come together and merge together. And when they do that, they give out a large amount of energy in terms of gravitational radiation. And the instruments called LIGO and Virgo have detected these gravitational waves in the last 3 to 4 years. And now we know several of these cases where about 20 to 30 coalescence events, so these merger events of two different black holes have been detected. So we have already known about these for a very long time. But these are what are known as the stellar mass black holes. So these are black holes which are formed from the remnants of the stars, and they're about the mass of a star. So they can be about from 3 times the mass of the sun up to 100 times the mass of the sun. So these are like what we call small stellar mass black holes. But the black holes that I like to study, these are actually much, much bigger than these stellar mass black holes. So the ones that I study are called supermassive black holes. So not just massive, but supermassive. And that is because they are millions to billion times the mass of the sun. So not just very 20 or 100 or 500 times the mass of the sun, or even millions to billion times the mass of the sun. And they don't live anywhere randomly, but they often live at the centers of galaxies. So they're almost all the big galaxies that we know actually have a black hole, a supermassive black hole in their center. And most of these black holes have been sort of found interacting with the galaxy and affecting the galaxy. Of course, as seen in the picture, the black hole looks to be quite big compared to the galaxy. But actually that is not true, in a sense that this is a very exaggerated image. This is artist's impression, and this is not to the scale. The black hole, although it's quite big and quite massive, it's actually very, very small still compared to the size of the galaxy. And remember, I mentioned that a black hole is not only just massive, but it's also very compact. So it's very dense. So it's very, very small object, which has a very big mass. So when you compress all this massive amount of stuff, so million times the mass of the sun or billion times the mass of the sun into a very small region, that's when you get a supermassive black hole. So although these objects are quite massive, they are very, very small compared to the galaxy. And if you want to give a comparison, a black hole to a galaxy is about as big as a virus is to a human. So you can imagine how tiny a virus is. You cannot even see it with the naked eye. You need to have a very powerful microscope to be able to see viruses. So in the same way, black holes are not easy to detect, and they're really, really small. And compared to a large galaxy, which are 10,000 or 100,000 light years across, a black hole is much, much smaller than even a single light year. And even our own Milky Way has a black hole in its center. As was mentioned by Anna in the beginning, that the black hole in the center is called Sagittarius A star. And we have detected it with telescopes, and it has a mass of 4 million times the mass of the sun. But how do we actually know that it's there? And today I will be discussing in short how this black hole was detected, and also how different black holes are usually detected in the centers of galaxies. So as you can see in this picture, our view towards the center of the black hole and center of the Milky Way is very crowded. There are a lot of stars, but also the view is blocked by a large amount of dust that you see in the center. So if you try to observe it, the Milky Way, if you go out in the village areas or outside the cities, then you will be able to see the Milky Way in the sky, very nice, bright belt of light that you can see. Especially if you go in the southern hemisphere, then you see it much brighter and directly over your head. But you will see that there are these dark patches in the middle, and that is the interstellar dust that is blocking our view to the center. And the problem is that then you cannot use your optical visible light telescope that we can see to study this center of the Milky Way. But instead, what you can do is you can use other wavelengths. So instead of looking at the center through a visible light telescope, you can use radio and infrared telescopes. And when you look at the Milky Way with radio, you see this completely different image. So this is the same center of so the Milky Way band, and seen with a radio telescope. And you can see that the center is very bright, and there is completely different view that you can see. So that tells you that there is some very energetic event happening at the center, and there is a lot of stuff going on. So people have observed this center of the Milky Way for almost several decades, and have found that the center contains a very compact object which is giving off a lot of radio energy. And that was one of the clues, that was that there must be something present there that must be something similar to a black hole. But the other thing that you can see towards the Milky Way is in the very, very center, within central 10 light years of the center of the Milky Way, you see a large number of stars. And these are the kinds of stars that Parshati was talking about. These are very massive stars. Some of these are red giants, and some of these are sort of in their late stages of life. And these are very also young stars. And these you can see through infrared telescopes. So something like the Very Large Telescope in Chile, or the Keck Telescope in Hawaii. So these stars have been observed for a very long time. And what you see also is that there are, in the very, very center of this image, are these small number of stars, about 20 to 100 stars, which are extremely close to the center. So extreme center of the Milky Way, where we expect the black hole to be. And these are the stars which people studied for more than 20 years. And what they did was they calculated the orbits of these stars. And as you know from the Kepler's laws of motion and Newton's laws of gravitation, if you measure how fast a planet is moving around a star, or how much one star is moving around other object, you can calculate how much mass is present in the middle of it. So by measuring the speed of these stars and calculating the entire orbit of these stars, astronomers studied these for almost 20 to 25 years to calculate the entire orbit. So some of these stars, so this is the orbit of the star called S2, and it takes 14 and a half years to complete one orbit around. And so they did these calculations and they found out that within the small region in the center, so the region that is as small as the distance between the Earth and the Sun, within that very small region, you have more than 4 million solar mass objects sitting there. And it's very, very small. So you can imagine just our Sun, which is quite small compared to the galaxy, but the distance between our Sun and Earth, it's 1 astronomical unit. And within that kind of distance, if you try to put 4 million suns, what will happen? So if you have that kind of massive object that is 4 million times the mass of the Sun, and you're compressing it in such a small area, what you get then is a supermassive black hole. So by observing these stars and how they orbit around these black holes, you can detect the supermassive black hole. And so for this kind of research, this year's Nobel Prize for Physics was given to Reinhard Genzel and Andrea Ghez. So this was an exciting discovery that happened. But not only in our own galaxy, but there are black holes found in many, many other galaxies. So in fact, as I mentioned earlier, we think that almost every big galaxy in the universe hosts a black hole. And one type of this black holes or one type of this galaxy is called quasar. So quasar stands for quasi-stellar objects. So when these objects were discovered in the 1950s and 60s, the telescopes were small. And for those telescopes, these objects looked like stars, but they were so bright that they would be brighter than an entire light of the galaxy. So if you combine 100 billion stars in a galaxy and combine all the light coming from them, many of these quasars were actually brighter, 10 times, 100 times brighter than that. And not only that, they were brighter, but they also were changing in their brightness periodically. And by studying how fast their brightness was changing and how quickly they were changing, you were able to tell that these objects were at very far distant. So they were in the far distance away from our galaxy. So they were not stars in our galaxy, but they were very distant objects, millions or billions of light years away. And they were very, very small objects coming from the center of the galaxy, that the changes, the variation that was happening in their light, that was coming from a very small region in the centers of those galaxies. And as you can see, these were also found out to be the supermassive black holes. So when you see those objects in visible light telescopes or in radio telescopes, or even better with X-ray telescopes, then you can see the extreme bright light coming from these objects. And what happens is that these supermassive black holes are sitting in the middle of these galaxies, and they are attracting a lot of gas and material around coming from the galaxy towards them. And as this material comes around, it sort of falls into the black hole, but it doesn't fall straight through. It forms a disk of material around it, just as Parshati showed about star formation region, where you have a planetary disk forming around the star. We call it also planetary accretion disk. Similarly, with black holes, you have this accretion disk forming from the falling material towards the black hole. And this disk is going around the black hole at very high speeds. And then because of high speeds and the friction between the atoms and the particles in the gas, it heats up very much. So the temperatures rise several thousands to hundreds of thousands of Celsius. And when the temperatures reach that much, it gives off a large amount of light. And this light is then detected in terms of radio light or X-ray light, or even sometimes invisible light. So this is one of the best ways, if you want to detect supermassive black holes in the universe, this is one of the best ways to detect that. And the other way is massive radio jets. So as you can see in this picture, you have this material falling in the form of an accretion disk, but something happens in the center towards the black hole that is shooting off a ray of light from the top. And that is what we call a jet. So this jet is given off. We still don't understand why these jets are present. We have very little understanding of what processes are leading to this accreting material to be launched out perpendicular to the disk and as a jet. But these jets are really, really powerful. And what you can see here is a jet from a galaxy which is known as Hercules A. And in the center of this image, you can see there is a sort of circular blob. And that is actually an entire galaxy. That's an elliptical type galaxy, which is about the same size or slightly bigger than our Milky Way. And these two jets that you see from coming from two sides of this galaxy, these are very massive jets. These are very powerful jets of plasma which are thrown off from both sides from the supermassive black hole. And these are so big that they span about 1.5 million light years. So when you compare that, our Milky Way is only 30,000 light years across. So you could actually fit along the length of this one of these jets, you can fit about 30 Milky Ways. So this is such a big amount of energy that is thrown off from this black hole. So one of the best ways to detect these kinds of supermassive black holes and the presence of these black holes is to observe them with radio telescopes and try to see these jets coming off from these black holes. And this is one of the ideal way of detecting black holes. And you see very beautiful, amazing jets coming from various different galaxies. And these are some of the most fascinating sights are present in the universe. And one of the famous examples of these jets is this Messier 87 galaxy, where you can see that on the top there is the core of the galaxy and from which this jet is coming off. But the galaxy has become more famous, not just because of this core and the jet, but recently it was the main target of the Event Horizon Telescope, which was used using the radio interferometry techniques that I study. We combined different telescopes across the Earth to form a single telescope the size of the Earth. And using this massive Earth-sized telescope, we were able to observe to the very, very center of the black hole. So what you see in this image is actually the photo taken of a black hole around the event horizon of the black hole. So from the very, very nearby region of the black hole. So what you see around here is the light going across the black hole and the central shadow around that is formed because of the black hole. And if you want to compare the size of it, here is a very nice cartoon that was done by XKCD, where you can see the span of our Milky Way. So, the span of our solar system, the sun in the center and Pluto's orbit around it. And the size of this black hole is about 10 times bigger than the size of our solar system. So this is one of the biggest black holes that we know. It's several billion, it's about a few billion times the mass of our sun. So it's one of the biggest black holes that we have found. And this was one of the targets of the Event Horizon Telescope, which studied the light around the event horizon of this black hole. And the way to understand this, how precise this measurement is like if you were standing in New York and you were looking at a coin, somebody holding a coin in Los Angeles, 3,000 kilometers away. So this is like, this kind of precision was obtained with this telescope. So in our day-to-day life, what we study are questions like, where do these supermassive black holes come from? So these are very, very big. These are not just forming from just stars dying and forming a black hole. There are some other mechanism that must be true, but we don't really know how they are formed. There are some theories around, but we don't really know how these black holes are formed. The other question is, when these black holes form, how do they grow? When they are accreting a lot of material, they're catching a lot of gas and dust from the galaxy, so they are growing quite big. But what are the mechanisms from which they eat a lot of this stuff from the galaxy and grow to be such millions and billion times the mass of the sun? And even more important question is, how important are these black holes for the formation of the galaxies, evolution of the galaxies, formation of life in galaxies, and what is the interaction between the galaxy itself and the black holes, and how do they live together in their life? So these are the kinds of topics that we study in our day-to-day research. And if you're interested in learning about those, you're always welcome to talk to astronomers, especially people who study supermassive black holes. And if you have any questions, you can always reach me here or on my website. So thank you so much.
Thank you, Abhijit. Really very, very interesting. And I myself learned a lot with you. Now we are going to continue our section with Elena Kilpio, who is also a mentor of this program, the Space for Human. Elena will tell us about what is Interstellar Extinction. Elena graduated from Moscow State University, the Faculty of Physics in the Astronomy Division. She worked in the Institute of Astronomy, RAS, at I'm at the Federal Agency for Science Organization. From 2016 up to now, Elena is Deputy Head of Support Staff and a researcher in astronomy and astrophysics at the Russian Academy of Sciences Department of Physics. Her main areas of interest are symbiotic stars and interstellar extinction. Go ahead, Elena.
Hello. I will give you a brief introduction to the interstellar extinction problem. When you look at the Milky Way at a clear night, you see a lot of stars, of course, but also there are big dark areas along all the Milky Way. What are they? Are they prey of stars? Or maybe it is something else? At a first glance, one can think that these are empty areas, but in fact, this is not true. Here you can see our Milky Way galaxy. Of course, it is an artist's impression. In fact, we can never see it as in this illustration, because we are inside it. We are here, near the galactic plane. We see our galaxy as it was shown on the previous slide. If you look at photos of other galaxies, rather similar to the Milky Way, for example, it is Andromeda galaxy, you will also see some dark areas on the bright background. In a galaxy that is seen from the edge as this one, you can see that dark areas are along all its diameter. In fact, the space between stars is not empty. There are dust, gas, cosmic rays, magnetic fields that form various complex irregular structures in interstellar space. And these structures, as well as the stars, are concentrated near the galactic plane. So the light from a star on its way to observer travels through this interstellar medium. And when it crosses a cloud of interstellar dust, it experiences scattering and absorption. The star becomes more dim or invisible at all for the observer. The measure of influence is not the same for different wavelengths. Blue light is stronger influenced than the red one. So the star looks redder than it really is. This effect is called interstellar reddening. The dependence of extinction on the wavelength is also called the extinction curve and looks like the following. This is the example of an area near the galactic plane. And dark regions, here they are dense dust clouds. The red stars are reddened by the dust. Some blue stars you see here are rather nearby ones, and they are located in front of dust clouds. That's why they remain unreddened. The interstellar extinction can significantly change the observed characteristics of a star or other astronomical object, for example, its spectrum. If we will neglect the interstellar extinction, we can get wrong characteristics when interpret the observational data. For example, we can get absolutely incorrect estimation of the distance to an object. This can lead us to wrong conclusions in our studies. So the question arises, how can we measure the extinction? How can we take it into account? Here is another artist's impression of our galaxy, as it's seen from the edge. According to very rough estimates, on average, in the galactic plane, the interstellar extinction in visual range is about 1.8 stellar magnitudes per kiloparsec. It means that the light from a star located at 1 kiloparsec distance from us is about 16 times weakened by the interstellar extinction. In direction to galactic poles, this value is much less, but it is also non-zero. Due to a very inhomogeneous distribution of absorbing matter, we cannot calculate the extinction values using any analytical formula that would be general for all the galaxy. Interstellar extinction varies with the wavelength in a way which is generally rather uniform along different lines of sight within the Milky Way, and can be characterized by the standard extinction curve that was shown at previous slides. However, the amount of extinction varies greatly from almost no absorption at all to many cases where objects are entirely invisible at optical wavelengths and can only be seen in infrared or radio wavelengths. For example, in the direction to the galactic center. So the way to construct some maps that will allow us to estimate the extinction value in a selected direction seems as a good solution. Of course, the problem of interstellar extinction is known for a long time, and for dozens of years there were a lot of attempts to construct interstellar extinction models and maps. Such maps were constructed using different objects with known characteristics from theory or defined by independent methods. They were models based on spectral and photometric store of data, on stellar clusters, star counts, galactic dust distribution models, many of them. They were also so-called two-dimensional galactic extinction maps, providing maximum value of extinction in a given direction. But they are not very useful for study of the objects inside our galaxy. They can be used for studies of objects outside it, for extragalactic studies. For dozens of years, there were a lot of attempts to construct interstellar extinction models. All the models using spectral and photometric data were based on a rather small number of stars. And of course, they couldn't provide precise data on extinction. That is why different models often give results that differ greatly. Here, the result of comparison of some old models for a select line of sight is shown. I constructed this picture about 25 years ago. You can see that the behavior of extinction according to different models differ greatly, and the results are very different. It is obvious that the more objects will be used for construction of a map, the more detail of space matter distribution will be taken into account, and the more precise estimates we will have. In order to construct a good three-dimensional model, we need good photometric data and big catalogs. Multicolor photometry is required for determination of interstellar extinction. Now we live in the epoch of big data. There are a lot of high-quality data covering broad spectral range for a huge number of objects provided by modern surveys. And they contain photometric data for billions of stars. These large surveys used in combination give us an opportunity to construct the detailed and rather precise three-dimensional interstellar extinction map that can become a useful instrument for usage in a wide range of astronomical studies. But the big work should be done before it will be realized. This work is underway now, and we hope that finally we will have a good interstellar extinction map. Thank you very much for your attention. Sorry.
Thank you. We now will continue with the questions from the chat.
Yes, sure. There are many questions, and I have some also. So we start with the audience here. The questions. The first one is about. It's the question from Lipset Dash. He's asking: a light takes many light years to reach a space telescope, so the pictures that we get are actually the old pictures of that star. Is that true?
So yeah, we actually, whatever pictures we're getting, depending on the distance of the object, you're actually looking in the past, which I think is like a mind-blowing fact in itself for space. So if you're looking at, let's say, the closest star to the sun, which is Proxima, it's like 4 light years away. So whatever you're seeing right now, you're seeing what it was like 4 years ago. And same way, a lot of these stars are, millions of light years away, and you were seeing them as they were at that time. So it is very true that you're looking at an old picture, and so this is an amazing thing. This is why we have to look at different stars at different stages of life, because you're looking at these things that once existed at that time, and then you piece together the whole mystery based on that. So yeah.
Thank you, Doctor. And the other question is, I go back to the questions. The other one is, black holes are always projected as a region which is completely black and states that even light cannot escape through the black hole. Is it a myth? And this from also Lipset Dash.
Yeah, so it's not a myth. That is completely true that black holes are essentially, as I mentioned, that the definition of a black hole is a region from which light cannot escape. So anything that is very compact such that you form a region, we call that the event horizon of a black hole. And if anything falls inside that, nothing will come out. I think there was a follow-up question to that, so they were trying to compare what the pictures that I was showing that the black holes were actually quite bright. But the difference is that what I was showing was actually outside this event horizon. So black holes are simultaneously the darkest and the brightest objects in the universe. It's a kind of a mystery in a sense that because these black holes attract a lot of gas around them, the gas heats up. Before it falls inside the black hole, the gas heats up and becomes really, really bright. But once it gets inside the black hole, inside this event horizon, it can never come out. So inside this event horizon is always black, and nothing will come out. So that's the first part of the question. But the second part is that because there is this large amount of gas that is outside of the black hole, that is what is making it really bright and one of the brightest objects in the universe.
Thank you so much, Doctor. Actually, I've seen on LinkedIn a question regarding the difference between a star and a planet, because we have different audiences. Actually, some audience, different audience. Some people they don't have a scientific background, and this is a way to spread knowledge. So they are asking, or the person is asking the difference between the two. Thank you, Doctor.
Thank you. I'm more than happy to. Obviously, you can jump in as well. So yeah, a star and a planet. Interestingly, we get this question asked a lot because, there are facts out there that confuse people a lot, whether Jupiter is a planet or a star. So a star is an object that basically is burning fuel in its center and generating all this light and energy and heat around it. Well, planets generally, and obviously I'll go into a bit about kind of the distinction between planets and star. There's a thing in the middle, what we call brown dwarfs, but the planets themselves don't generate, they don't burn hydrogen in their core that generates all of these energy and light and heat that you see from the stars. And so the major distinction is when you look at planets, they're reflecting light of, whatever star or object they're around. Same with moons in many cases. But the thing is that planets are going around a star and they're generally forming out of the same material that is surrounding the star when it's actually forming. So that's kind of one of the key distinction between the two. Now, a lot of the times people say, oh, but Jupiter is like very massive. Can it be a star? It is actually if Jupiter was 13 times more than what it is right now, then we would have a second star in our solar system. But it's not that massive to be able to take all the hydrogen it has and burn that in its core to make it a star. So so there is this set of stars, or I guess category right in the middle of the planets and the stars that we call brown dwarfs, that are basically really interesting objects that are at this cusp of either becoming a planet if they were too small, or a star if they were too big, but they're right in the middle. So that's the distinction. I don't know if Abhijit has anything else to add to that.
So I think the only thing that you can talk about is this borderline between the stars and planets, these brown dwarfs and failed stars, that some of them we don't really know whether they are stars or not, because there might be some small amount of burning happening in the center, while the outside looks like a planet, but it's quite kind of a borderline between that. So yeah.
I think the simplest way I need to add to people to understand that the simple way to explain it is that planets simply reflects the light from the stars, okay? They don't have emissions. It's only reflection, like a mirror.
Thank you. Thank you. Thank you. I have one more question if we still have time.
Yes, go ahead.
Okay, the other question is, well, as stated by Dr. Abhijit, black holes contain millions of stars. The question is, what phenomenon makes them to come together to such a compact unit?
Yeah, that's a fantastic question. The current problem is that we don't know how these massive supermassive black holes form. We have multiple different theories, but we don't know exact solution to those. So there is a possibility that you could start with a normal stellar mass black hole, so a small black hole, which is maybe 20, 50 times as massive as the sun. And then it grows by merging with other big, small black holes, or by eating up a lot of gas and then growing to be a really big, massive black hole. The problem with that is that it takes quite a long time for a small black hole to grow to be quite big, and the universe doesn't have that much time. So we see already a lot of these massive black holes, which are billion times massive than the sun, formed already when the universe was only 1 billion years old, or even younger than that. So these massive black holes were already formed when the universe was very, very young. So they did not have enough time to form from these gradual evolution from small black holes and eating up a lot of gas to form big black holes. So the alternative theory is that you could have a large gas cloud, which is about 10,000 times or 100,000 times the mass of the sun, that itself collapses directly into a black hole, and then that could form 1 million times solar mass black hole. So these are kind of current theories that we have for formation of these massive black holes, but we don't know which one of these theories is correct.
Thank you so much, Doctor. This would lead to my question, actually. I think I still have a little bit of time. The question is, you said that you are still, or scientists and astrophysicists, they are still speculating with the formation, about the formation of black holes. And one thing, I'm not a scientist, and I got into this black hole world and gravitational wave and so on. And the question is, because I'm making some research about it, the question that I have in mind is, do you think that gravitational wave detectors, and especially this new European Space Agency, LISA, will solve a lot of these mysteries that you are after and you are trying to solve?
Yes, that is definitely true. So one of the clues to this mystery would be detecting what are known as intermediate mass black holes. So I talked about the stellar mass black holes, which are like 3 to 100 times the mass of the sun, and the supermassive black holes, which are million to billion times the mass of the sun. So there is still gap in the middle. You have between 100 to 1 million times the mass of the sun. So this is this region is called as the intermediate mass black hole range. And these are sort of theorized black holes for which we don't have concrete evidence of existence. So one of the ways you could solve this problem is if we detect these kinds of intermediate mass black holes in the universe, and knowing how abundant they are, how common they are, and understanding how they live in the universe, then we might be able to understand how they might grow into the big black holes. So this detection of intermediate mass black holes would be facilitated by the European Space Agency's LISA mission. So one of the main targets for the LISA mission is these intermediate mass black holes. But also recently, one of the discoveries from the LIGO instrument was of the detection of a black hole, so they detected two black holes, which were 65 and 85 times the mass of the sun. And they came together to form a black hole, which was about 130 solar mass black hole. So this kind of a black hole is on the lower boundary of this intermediate mass black hole. So we already are starting to see some evidence of these intermediate mass black holes. And with further observations with LIGO and LISA, then we will be able to detect these intermediate mass black holes, and they would be the clue to understand how these supermassive black holes form.
Thank you so much. That's very interesting. And actually, I can imagine that it's for scientists, these technologies are like the gift for Christmas when you are discovering new discovery, and there is a new technology that is going to open up a new dawn for you. It's like the Pandora box for you. So it's very exciting times, I think.
Yeah, that's absolutely true. That especially with LIGO and gravitational waves, that is a completely new ways of understanding the universe. So far, we have only been observing the universe with light, but now gravitational waves gives us a completely different tool. So it's like working with a hammer all your life and then discovering a modern equipment. It's completely different kind of experience. So yeah.
That's exciting. Thank you so much. Thank you.
May I have a question? One more?
Last question.
Last question. Yeah, Parshati, maybe you can add a little more about the star formation rate, if you have done some calculation, and which are the indicators you use it to do it. And also, I understand that your research was on the nebula only. Yes? Maybe you can add a little more.
Yeah, so I actually did not study star formation rate. My researcher is very much studying the disk and the star itself. And this is why I was only able to study 4 stars, just because of the amount of coding that goes into making those stars and disks around them. I did have friends who studied star formation kind of in the similar regions that I was looking at. And I studied the stars that I did study. They were all in the Milky Way. They were not only just in the Orion Nebula, they were in other regions as well. But I like showing Orion Nebula because it's so pretty, and it's like one of the easiest, if you have a small telescope, it's one of the easiest nebulas to see as well. Yeah, so, I would love to study star formation rates. Unfortunately, I only had 4 years. So, yeah.
Okay, thank you. Okay.
Well, thank you, everyone. Thank you for your active participation. Especially thank you for the panelists, our raving fan, show fan, and moderator today, Anna. I know you were there from day one and continued to be with us. Thank you for our participants for the interactive and thoughtful questions. I'd like to share with you and actually encourage you to follow up. Please send us your comments, your advice, and any recommendation on how we can improve this Space for Women network. There's no such thing as too much information, particularly when it comes to the future of space exploration and science. So thank you, everyone. We're looking forward to welcoming you to next Saturday, Series 30, with some very special guests again. Will quantum technology make the next giant leap of the evolution of civilization from Earth to our space? With Dr. Yogesh Malhotra and Sonali Mohapatra. She's a space quantum technology developer, and Clarice Galileo. She's a quantum engineer. So once we get off here, within the next few hours, you're able to register for next week. Thank you, everyone. Stay safe, stay healthy, and we shall see you very, very soon.